Okay, so let's look, for example, at this image. So here you see, I don't know how easy or hard it is to see, but there are some cylindrical obstacles here. So these are dark cylinders. And you have a uniform flow of particles going in, and these uniform particles would be going through this array of obstacles. But instead, you see that all the bright stuff is focused on the left-hand side of this array. And this is what you see in this device when the voltage is very high. If the voltage were low, you would just see these particles zooming on through. And this is consistent with the idea that these particles are experiencing a negative dielectrophoretic response. In fact, if we solve the Laplace equation in this array, we'll find that in regions right here, or here, or here, or there, the magnitude of the electric field is high, higher than this region out here. So if I move from this region here to this region here, there's a gradient of the electric field squared. And if particles experience a negative dielectrophoretic response, there's a force that prevents these particles from entering that obstacle array. So these particles are all zooming in from left to right, and they basically get trapped at the inlet to this array owing to the negative dielectrophoretic force. And so this and this and this, these are all three different examples of very similar phenomena. They're all examples of particles, or in this case cells, moving through a device and having their location be affected by the dielectrophoretic force. And this is interesting, but I will argue that this is useless. And the reason why I think this is useless is taking particles and having them get clogged somewhere because of a dielectrophoretic force isn't really any better than having them get clogged somewhere just because they got clogged. Right? So this is cool, and this illustrates physics, but I don't think this is really very practical. And in fact, it points out a fundamental limitation in dielectrophoresis, in that it's easy to tell the difference between a positive response and a negative response. But if the only thing you can tell is the difference between positive and negative, the best thing you can do is you can sort out two different things. You can tell the difference between a red blood cell and a white blood cell, but that's about it. So we were motivated to take these same ideas, but to come up with geometries that were cooler. And so Ben's idea looked a little bit like this. The idea was that he wanted to have a device where particles could come in. He could have a dielectrophoretic force, but this dielectrophoretic force would actually change with location. And the fact that this dielectrophoretic force would change with location would end up leading to particles being sorted to a specific position that was a function of their dielectrophoretic mobility. And let me see if I can motivate that and then come back. Okay, so let's look at these simulations. So what you see is a wall. These are simulations. The wall is colored in this weird green color. The domain itself is the stuff that's in this grayscale. And the whiteness of the grayscale communicates the magnitude of the electric field. So my first question is, why is it black here but gray there? Ah. Could you say that again? So the electric field is strongest at the corners, and you can see strong signal there and there. But it's also just brighter here, even away from the corners. It's brighter there than it is there. Why is that? It's a uniformly conductive electrolyte solution. Why is my electric field stronger in the middle?
Because you're dropping the same voltage between the top and bottom across the entire thing.
So let me be clear about the boundary conditions. So the wall, bottom and top are insulators. I'm applying a voltage here at the left and a different voltage here on the right.
Because the electric field lines have to come together there.
Absolutely. The electric field lines have to come together. We have to satisfy conservation of current, right? So if I have a large area here, I have to have low current density here and low electric field. Here, my cross-sectional area is lower. My electric field lines had to converge. I have to have a high local current density. What does that mean? It means that any time I make a bump on a wall in a microfluidic device, I'm creating a localized region of high electric field. If I have particles with a dielectrophoretic response, they'll then be attracted to or repelled from this region of high electric field, and that allows me to actuate particles. So this is an example of what particles will do if there's no dielectrophoretic force. They zoom in, they go through. You see that they go faster when they go through this constriction region and the electric field's higher. But that's basically it. right? Nothing exciting there. But if there's a negative dielectrophoretic response, they go in, and despite the fact that the fluid's moving from left to right, there's a repulsion. There's a negative dielectrophoretic response causing these particles to move away from the region of high electric field. Right? And this is something that you can do in simulation, and this is something you can do experimentally as well. Anyway, that's something you can do experimentally as well. Okay, so given this is the top view of a simulation, this is the top view of an experiment. What you see in the experiment is basically the same as here, except there are some complications because this simulation is ignoring some physics. This is the real experiment, which has some of the complicated stuff. But the bottom line is, in both this case and this case, you see particles clustering in this region. So this is really no different from the thing that I showed a couple slides ago that I said was useless, right? It's just something where stuff clogs up. But if you take this and turn it on its side, now you can start thinking about this in a different way. If I put a bump on the bottom of a microfluidic device, that creates a localized region of high electric field. That region of high electric field creates a force that acts normal to the bump. So now if I have a microfluidic device, I have particles that are moving through the device. There's some global solution of the Laplace equation that tells me how they move. But then on top of that, everywhere where I put a bump, there's a force normal to the bump. So now I can make a device that has one shape that shows me grossly how the fluid moves and how the particles will move if they have no dielectrophoretic response. And then in addition to that, now I can put a whole bunch of stripes in a variety of different patterns in this device. And everywhere where I put a stripe, there's going to be a normal force that's going to change the way particles move. And that leads to a result that looks like this. So this is now, again, flow from left to right. It may or may not have a video. Oh, yeah, look at us go. Sweet. Okay, so what's the idea here? We have insulating walls at top and bottom. We have a voltage on the left and a voltage on the right. A number of particles are being sent through, and these particles are color-coded to indicate their dielectrophoretic mobility. And by dielectrophoretic mobility, I mean, one, a measure of the dielectrophoretic force that is applied to it, but then that has to be normalized by how hard it is to move the particle. So dielectrophoresis scales, for example, with the radius cubed, the dielectrophoretic force. But the relation between that force and that velocity is also proportional to the radius of the particle. So you find that the dielectrophoretic mobility, which we could denote with an expression that looks like this. This basically is a relation between the gradient of the electric field squared and the dielectrophoretic velocity. This has different units from the electroosmotic or electrophoretic mobility. This dielectrophoretic mobility, we'll find that this is proportional to the radius squared. And the reason is because the dielectrophoretic force is proportional to a cubed, as we've discussed in recent lectures. But it's also true that the Stokes drag on a particle, so a sphere moving in Stokes flow, the relation between the difference between that particle's velocity and its surrounding fluid, the whole idea is we're applying a dielectrophoretic force and we're making this particle move relative to the fluid with a velocity. The counteracting Stokes drag force that we feel when that is happening is given by 6 times the velocity times the viscosity times the radius times, what's the last thing? What's that? Thank you. So because the Stokes drag is proportional to the radius, the DEP force is proportional to the radius cubed, this dielectrophoretic mobility ends up being proportional to the radius squared. Okay, so these things are all color-coded with this dielectrophoretic mobility. Now, this device has a little bump here and a little bump here. And so as I showed on previous slide, the presence of a bump leads to a local region of high electric field. That local region of high electric field, if the particles are negative dielectrophoretic, causes a repulsion. If that repulsion is big enough to prevent it from going over the bump, when I turn this on, the fluid all goes straight from left to right, but when these particles come in, they experience this bump, and they can't get over the bump, so they just slide along the bump until the bump ends right here. Then they come across here, and they hit this bump, and they slide across this bump as well. Except now this bump is curved, and particles of different dielectrophoretic mobilities, relatively low, medium, or high, now fall off at different y locations. These particles are coming in, sliding up, going there, coming here, and now they all fall off at these different locations. Now, why will they fall off at different locations just because the second bump is curved? What's that? Fractionation? At least at the moment, I don't see the link between field flow fractionation. I mean, field flow fractionation is where you have particles that move at a different velocity based on how close they are to a wall, and their proximity to the wall is a function of some tangential force or some normal force. I don't think that's quite what's going on here.
Could it be because the the curve?
Yep. Student. Okay, I'm done. You can talk now.
If it's the curved surface, will not give you like the almost like constant electric field that we get the other parts, because it's curved and you will have changes in your electric.
That's exactly right. Right. So what I showed you a couple of slides back or forward, depending on how you look at it, this was what happened if I had a bump that was normal to the flow direction. If I have a bump that's normal to the flow direction, if I take the surface area and I divide it by 3, my electric field goes up by 3, and that's it. But if I take this bump and I put it at an angle, now the normal part goes up by a factor of 3, but the tangent part is the same. So the net effect is that if I have my bump normal to the flow, the electric field goes up a lot. If I have my bump at an angle to the flow, it doesn't go up as much at all. And that difference ends up being described by a cosine of the angle. Here we go. Yeah, so now this is close to normal. So if I assume this bump is taking up half of the area, this electric field goes up by 2. Here the electric field goes up by maybe 1.8. Here it goes up by 1.5. Here it goes up by 1.3, 1.1. So here the electric field is pretty high, but the red stuff still falls off because the red stuff has a low dielectrophoretic mobility. The orange, the yellow, the green, the blue, here at this electric field, which is, let's say, up by a factor of 1.8, there's still enough force that prevents it from falling off. But I get down here, now that electric field has only gone up by a factor of 1.5, the magnitudes of the electric fields are smaller. The gradient of the squared electric field is smaller. The total dielectrophoretic forces are smaller. And so now the orange stuff can fall off. I go down a little bit lower. Now the electric field is lower. The yellow stuff can fall off. Green, blue, etc. So all that's going on here is you have a bump that perturbs the electric field. But then you use a simple technique to make that bump have a continuous variation in how much the electric field is going. And so now instead of binary sorting, you have what we call dielectrophoretic spectrometry. The idea being that, okay, whatever comes out here must have a dielectrophoretic mobility of 1. Here it's 2, here it's 3, here it's 4, here it's 5. And this is now a continuous function of the particle properties. And the reason why we think that this is relevant to sorting of Mycobacterium, which is what I started with, is you want to be able to take a broad population of Mycobacterium cells and sort them out based on how funky their membrane is. Because those cells that have the funky membranes are the ones that are more likely to inform how antibiotics or combinations of antibiotics can be used to kill those cells. How am I doing for time? Can someone help me?
3:55.
That's super awesome.
I have two questions.
I would like to hear both of your questions.
Did you choose a curve to ensure that there's no circulation and you separate the flow? And when do we get to see the second process?
So the first question is, why did we choose the curve?
Instead of just like the slope.
So this is the thing, a slope. So if this was just at an angle, right? So this just went like that. If this were rectilinear, then the magnitude of the electric field would actually be the same everywhere. And the second one would look just like the first one. So the particles would come in, they'd slide along, they'd hit the next one, they'd slide along, and they'd all come out the bottom. What we need is, over the distance of this curve, we need the magnitude of the electric field to change, and so it has to have curvature. It has to be at a different angle relative to the global electric field. Oh, I'm sorry, I want to answer your second question. You will see the second uniform when I pass back graded materials. Sound fair? Okay. As I said, I can't read body language, so I have no idea if you're mocking me or smiling at me or whatever. Yes. Would you like to mock me? Yes.
Can you just go over how the earlier geometry that we have is different from this geometry? It just appears that both has a bump, and the electric field in the slot between the wall and the bump should be higher than in the other bump.
So there's no doubt that it's all just bumps. So the difference is that if you think of the system being two-dimensional, then you create some sort of constriction. That constriction creates a region of high electric field, and that region of high electric field stops particles from going into that region. If you now say, okay, well, I'm going to have a localized bump, so now in some z direction I'm going to have a little bump, but now the orientation of that bump can be thought of as being different or separated from the bump. It's really more of a 3D way of thinking about it. So I don't think of these things as being different so much as one is a very simple version and one is a slightly more complicated version. One is 2D and one's 3D. Is this helping or not really? Okay, fantastic. So let's go back and point to specific things. So this says that if I have a constriction, I can trap stuff. But all I could do is trap it, right? And in fact, the image I'm looking at is a top-down, basically a 2D measurement of what's going on. Right? I have no additional degree of freedom here that lets me take all this stuff that's trapped and send it somewhere. So if I take this, and rather than looking at it from the top and having constrictions in this field of view, if I turn it sideways and say, okay, now I want to look along the side of my microfluidic device, and now I want to make a little bump. Here I've made a little bump. So if this went all the way from the bottom to the top of the micro device, there would be a physical obstruction to the particles moving. And what you would see is my electric field would be low here. It'd be very high here through this gap. Right? And if this bump went all the way from the bottom of the top to the device, my electric field would be low, would be very high here. All the particles would go up. They'd speed up and go around here. They'd come down here. They'd speed up and go around there. And then they'd come out the end. Right? And if I had a dielectrophoretic force in that case, the particles, when they were going through this constriction, would be repelled, and they would basically just sit here. And nothing further would happen. So here, I'm constricting things in 2 dimensions. Here, if I constrict things in 2 dimensions and I make this bump go all the way from the bottom to the top, all I do is I make a constriction where the particles stop. But if now I have a bump that goes up 50% of the way or 90% of the way from the bottom, now I have a region of electric field. The fluid can still go over this bump. The current can still go over this bump. In fact, this bump is only a small perturbation to the 2D solution of the Laplace equation. To a first approximation, my solution to the Laplace equation in the xy plane is that it's basically uniform. The only difference is that the electric field is a little bit higher here, and it's a little bit higher here. And in fact, that perturbation is biggest here, next biggest there, and then it gets lower and lower and lower down here until where the perturbation is effectively 0.
So this is not just in z direction, this is not all the way to the top.
That's correct.
It exists halfway.
That's correct. And that's a critical part of it.
Yes.
Sweet. Yes, McCool.
How would this device behave if you throw the particles in the reverse direction?
You tell me. I have totally done it. Ah. Quandary. Yep. Well, what'll happen here? So I got particles coming in. What happens here?
Wait, that curve goes all the way down? Or?
This curve goes all the way down to here. So now I have particles of all colors. The blue ones are the ones that respond the most. They have the highest Clausius-Mazzati factor. The red are the ones that have the least. So now I'm going to take a rainbow of particles and I'm going to move them in from right to left. And they all come in here. What happens down here? Nothing stays there. So I would have all these particles and they would all go through. And then they would get here. And what would happen here?
Oh, but isn't that bump in place?
There's a bump here. And there's a bump here.
No, I mean, how would the particles go through the bump?
So right here, so you see, this is the first point where a red particle could fall off. Here, the red particle could have fallen off, but it never even got here. The orange particle is falling off also. So red falls off here, red and orange falls off here, red, orange, and yellow falls off here, red, orange, yellow, and green falls off here, and everything falls off here. By extension, down here, the perturbation in the electric field is so small that all of the particles will go over this ridge. So multiple colored particles, they went here, they would all go over this ridge. They would experience a dielectrophoretic force, but it would be too small to stop them from going over the ridge. Then they would putter along, boop, 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 boop. They would get here, and what would happen here? They get stuck, right? So my particles, all colors of particles would go here and get stuck. Okay, now let's say I take a rainbow of colors and I send them in here. What happens along this path? That's right, blue gets stuck, but everything else goes. So what I have is a system where every color goes through here. Here only the blue is taken away. Here the blue and the green is taken away. Here the blue, green, and yellow is taken away, etc. So what I would find is that all of, let's see, how would this work? All of the blue from here to here would get clogged up here. All of the green from here to there would get clogged. All of the yellow from here to there would get clogged. Meanwhile, everything that didn't get clogged up here would go through and would end up getting clogged here. So if I run it backwards, I get a clog of particles here and a clog of particles there. But neither of these clogs of particles is unique in any way. They all have a mix of different colors.
No, now I'm confused.
Super.
Don't we have that bump sitting there? How would it go through the... I don't understand the design of the system.
Okay, so I get that you don't understand it, but what are the key outcomes that contradict your understanding?
I think I can answer one.
That there is a slope there. There's a solid surface that does not stop the particles from going through.
So at no point in this device is there an obstacle that goes all the way from the bottom to the top of the device. There are only little bumps in the bottom that cause local increases in the electric field. So on the left, you have a bump that's at a sharp angle.
It will go over the incline, like out of the plane of the board.
Yeah, so particles are coming along here. If the electric field were really, really low, like let's suppose I run this thing and I just turn the electric field all the way down, right? Now the particles are moving slowly. There's no dielectrophoretic force when the electric field goes down because dielectrophoresis scales with electric field squared, right? So I got a bunch of particles. They would all go and they would go bloop and they would go over the ridge. And then they would go here and they would bloop and they would go over the ridge again, right? That's at low electric field. If I crank the electric field up, now my dielectrophoretic forces are going up with electric field squared. and my other forces are going up with only electric field to the first power. So now the dielectrophoresis starts to dominate. So I turn the electric field up and up and up, and now this stuff goes here. The dielectrophoretic force is so strong that now it can't go over, and now it slides along because there's a component of its force that makes it go. Is this helping? Fantastic.